Assalamu alaikum, everyone. This is third lecture on chapter 10, frequency response techniques. Uh, we actually, in the last class, we have discussed the phase margin and the gain margin. So today we are trying to further extend our idea regarding the frequency response. And the first topic that we are going to cover is the relation between the closed loop transient and the closed loop frequency response. So how they are related, if we try to figure it out, then we actually have to start with the unity feedback system of an ideal second order system. And this is your closed loop transfer function of your unity feedback system, the closed loop transfer function. And from this, we can find out what will be our magnitude value. So magnitude value is this one. Now, if you want to find out the peak value here, peak magnitude here, then what do you have to do? We have to differentiate the magnitude with respect to d omega square, and then we have to set it to 0. And that will give us this condition. Omega peak is actually, sometimes it is also known as resonance frequency. So this is the value that we are going to find. And now if you put this value into this equation, then we are going to find out the maximum value of the peak. MP is 1 by twice zeta root over 1 minus zeta square. So if from this equation, what we know is that peak value is also a function of zeta, and also we know that our zeta percentage overshoot is also a function of the zeta from chapter 4. Okay, so chapter 4. So from these two, if we can figure out for same value of zeta, what is the value of the NP and what is the value of percentage overshoot, and then if we plot, then we are going to get a curve like this. So this is indirect relationship, basically graphical relationship of your peak value of the frequency response with your percentage overshoot. So this is how we're actually relating the closed loop transient behavior. Transient behavior is percentage overshoot with that frequency response behavior is the peak value. One thing we have to be careful is if the value of the frequency, the peak value is this one. So if the value of the omega, if you vary from 0 to 0.707, then we will always have a peak value being found. Okay, so peak value will be found there. But if the value of omega is greater than 0.70, if the value of the zeta is greater than 0.707, so we are actually giving all these in terms of not in omega, rather it is in terms of zeta. So if the value of zeta is greater than 0.707, as you can see here, the frequency will become imaginary. So because this quantity will be becoming negative. So imaginary frequency is not possible. So we plot the real value of frequency in an imaginary axis. So, but imaginary frequency is not possible. So that is why if the value of the zeta is more than 0.707, so there will be no peak value in your frequency response curve. Now, yeah, you should not be confused about this limiting value of 0.707 with 0 to 1 in case of your underdamped oscillation. So they're actually totally different. This is related to the peak value of frequency response, and this is actually the limiting value of your underdamped, so time domain restriction. And the first one is actually frequency domain restriction. Now the next one is the relation between the speed and the closed low frequency response. So for this one, whether you have noticed or not from the first figure here, one parameter we haven't discussed, this parameter. Okay, so this is what is called bandwidth, and this is what is called your resonance frequency or peak frequency. So what is bandwidth? Whatever your zero frequency, zero magnitude, 0 dB magnitude, from that one, if you have a 3 minus 3 dB, or in normal magnitude 0.707 of your unity magnitude is there, then this whatever the corresponding from this magnitude, whatever the corresponding frequency that we are going to get, that is actually our bandwidth. So we are going to see that this bandwidth is actually related to our time domain parameters like your setting time, peak time, and rise time. So let us try to see that. So if you put magnitude equal to 1 by root 2, or if you place minus 3 dB into that equation. Okay, so in that case, what we are going to see is place the value here. Okay, so place the value here, and then if you derive it, then we are going to find that our omega bandwidth frequency is something like this. I'm skipping the derivation, but the derivation is fairly straightforward. So if you fail to find out the derivation, then actually you can do the reverse way. You start from this equation, then try to go into that equation, so it will be helpful for you. So now, as you can see, the bandwidth frequency is related to your natural frequency, and we know that we have a formula, or natural frequency is related to the settling time, and also natural frequency of oscillation is related to the peak time. So we are replacing the value of omega by settling time and the peak time. So that is how we can relate our speed of our transient response with the bandwidth of the frequency response. So based on these two characteristics, if we plot the uh, normalized bandwidth times your settling time with respect to the damping ratio, and as well as normalized omega bandwidth times your peak time with the damping ratio, basically based on these two equations, then you will have plots like this. At times, it is better to use the plot than actually going to find out it analytically. Because so it sometimes give you advantage over doing the repeated calculations. So what about the rise time? From the chapter 4, we know that there is no direct relationship. So rather we will have a relationship like this here. Okay, so with the normalized rise time with the natural frequency, and based on that, if you know for any particular value of say zeta. Okay, so we are just taking this value of zeta. For this value of zeta, this is our normalized rise time, and normalized rise time is actually basically it is rise times into the natural frequency. So if you do actually you have to find out the natural frequency, then you have to plot it here so that you can find out what will be your bandwidth. So in that case, say your rise time is 0.2. So what will be your natural frequency then? Natural frequency omega n will be 1.463 divided by 0.2. So now you know natural frequency, you already know zeta is 0.4. So if you put it here, then you're going to find out the corresponding bandwidth, which will be approximately 2.01 as it is shown here. So this is how actually you're converting this curve into this curve to find out the relation between your bandwidth and the rise time. Okay, now here sometimes actually so far what we have discussed is actually we figure out the polar plot or the board plot of the open loop system. So we try to find out the relation between the now we'll try to find out the relation between the closed loop and the open loop frequency response. So whatever the open loop frequency response we have figured out so far, actually we want to relate it to the closed loop system without directly applying the frequency response of the closed loop system. So actually this idea was developed whenever there was no MATLAB program. So nowadays it is actually not that necessary to learn about all this because of the fact that now we have the math lab, so we can directly give our closed loop system equation, and based on that we can actually find out the frequency response. But earlier we don't had that, so because of that we are actually trying to uh, find out a way to relate our open loop response that we already obtained initially at the beginning of this chapter with our closed loop, so that actually we can find out the closed loop response based on your open loop response. So, but we have to be careful here. So we are dealing with basically non-unity feedback system. So this discussion is basically for unity feedback system, not for non-unity feedback system. So for the non-unity feedback system, what can be done? We can actually give a hint of that. So for our discussion, we will limit it to unity feedback system. Now look at here. This is our closed loop transfer function of the unity feedback system. Now for the frequency response, we are replacing s by j omega, and we're just assuming that our g of j omega is actually complex number, so it has real part and the imaginary part. So if you put it there and then you try to find out the magnitude value, then you are going to find the magnitude value something like this. Now if you rearrange the equation a bit, then we are actually going to get equation like this, which is nothing but, as you can see, that x square plus y square equal to r square. So basically this is a circle equation. So origin of the circle is actually minus this value and 0, and the radius of this one is actually root over this value. So this is what is being written here. So for different values of m, actually we can find out this sort of curves. So these curves are called constant n circles or constant magnitude circles. So now one thing I have to be careful here is if the value of m is 1 here. So if the value of m is 1, then actually we cannot find, we can see that it will be becoming an equation like your equal to minus half. So basically it will be always a straight line like this. So for smaller values of m, we are moving in this side, okay, and for higher values of m, we are moving in this side. So you just maybe trial with one or two example of m value, and then we are going to see that this is what we are going to get. So these are actually the M circles, or basically the magnitude of the closed loop transfer function. So similarly, actually we are going to see there is also phase circle. So those are known as N circles. So these are actually magnitudes of closed loop transfer function. So if we have open loop transfer function, open loop frequency response, and we have this kind of curves, circles, then actually you'll be able to figure out the closed loop response. Okay, so the phase value is 5 from the same equation. So you will have imaginary excess component by the real excess component, tan inverse, minus this imaginary excess component by the real excess component. So tan inverse, so tan A minus B. So for if you apply the formula for simplification, this is what is becoming. Now, if you take the tan in the other side, tan phi is becoming n, and n equal to, we assume that tan phi equal to n, and then you have here q. If you just put the value, then you will have simplified value like this. Now, if you also rearrange the thing, again we are getting a circle. This time we will have a origin at minus half and minus 1 by n twice n, and this is our root over this one is our radius. So if you plot those curves, then we are going to get a phase curve, constant phase curve like those. Okay, so we have a negative value of the phase curve in the downwards, and the positive value of the phase curve goes this way. So this is also actually phase of closed loop transfer function. So now if we have both of them together, then we have something like this. This is constant n curves, and this is constant n curves. So if we now plot our basically for this particular example, they have based on this equation, we figure out what is the value of our Nyquist diagram. So Nyquist diagram, and then we superimposed the Nyquist diagram of the open loop system on this M and N circle. So then we try to figure out all the intersection. There's two ways to actually now figure out the closed loop response. One way is the polar plot. So basically polar plot, which is shown here. So say we are willing to find out this intersection point. So in this intersection point, the magnitude curve that is being related is this one, which is actually 1.3. And the angle that is being related here is actually -40. So if we just plot this one and then find out the angle of this one, then actually using a -40° angle and using a length of approximately 1.3, this length is being drawn. So you have to take for each and every point, and then you have to find out this whole curve. So this is actually the polar plot of your closed loop transfer function, but not necessarily actually you can say that this is the Nyquist diagram. So we cannot apply the stability criterion on this one. So it may not provide us the correct response. But more generally, why these M and N plots are used is basically because of figuring out separate magnitude and the frequency curve. So as you can see here, the intersection between, so at omega 1 we have an intersection, at omega 2 we have an intersection, at omega 3 we have an intersection, at omega 4 we have an intersection, at omega 5 we have an intersection, and finally the last value. So corresponding values, actually it is giving 1.1, then this curve is 1.2, then this is actually the curve's magnitude is increasing 1.4, then it goes actually touching this one, which is 2. Okay, so this is how we are figuring out the magnitude plot based on this diagram, the frequency, corresponding frequency, and the magnitude we are plotting. Similarly, to figure out the phase on the same diagram, so what you can see that the first case you have actually have a that omega 1, you are actually having around -10, something like this, and here you have intersection with -20, so correspondingly -20 is here, and then -40 around here, then you have so -60. So this is how you're going to have your phase plot. So from this M and N circle and the open loop frequency response, we can actually figure out what is the magnitude and the phase of our closed loop transfer function. But remember, this is for unity feedback system only. So for the non-unity feedback system, what should be the approach? This implies for unity feedback system. So what you have to do actually, you have to somehow convert it to unity feedback. So basically, non-unity feedback, we have 1 plus GH. So we have to multiply with H here. So now it is almost similar to the equation G1 plus GH. Okay, so you can actually apply the same formula here. After finding the result, so whatever the result you are getting, so that our result has to be again divided by H to figure out the actual response. So this is a trick that we can apply for this ML and circle method. Okay, so the problem with the M circle is basically that the gain is not in dB, rather the gain is in a simple magnitude. So for that, like if you try to plot the board diagram, then board diagram is actually in the logarithmic scale. So, and because of that, it is very difficult. So like in the logarithm scale, if the gain value is changing, so what will happen? The curve will be either moving up or down, because in the logarithm scale, this is just addition. So higher value is actually moving up, the curve is moving up, and the lower value of the gain, the curve is moving down. So it cannot be easily incorporated in the M and the N circle. So that is why Nicholas designed a special chart which is based on your M and N circle, and M is actually magnitude is in dB. Then they are actually having circles like this. So these are your magnitude circles, and also the N phase. So magnitude versus phase, he just mapped those M and N circles, and he generated this chart, and this is known as Nicholas chart. Another version of more clearer version is being shown here. So this is also based on actually unity feedback. This is one of the drawback of this thing is always we're going for unity feedback. So for this one as well, so basically it is starting from, whole diagram is also not shown here. So from basically 0 to 360 degree, whole range of phase is actually being shown here, and also all corresponding magnitude. The idea is basically same. Whatever the open loop diagram that you, frequency response that you have, that you have to superimpose on this one, and you have to find out the intersection points, and those will give you the corresponding value of the closed loop loop frequency response. So as you can see, for different value of gain, this is for gain equal k equal to 1, and this is for k equal to 3.16, and they have plotted, and they have different intersection point, as you can see, and based on that you have to find out the magnitude as well as phase. So sometimes phase will not be exactly in that figure, then you actually have to approximate the curve, what will be the next curve. So it is in between 20 and 40, so and also closer to 40, so we can say that this is actually on minus 35 curve. Okay, so this is how you have to find out the angle, as well as you have to approximate the magnitude. So it is in between 1.4 and maybe 1.3, so closer to 1.4, so maybe 1.38, something like this. So this is how you have to figure out the intersection points corresponding frequencies as well. So for more clear view, actually, as you can see here, for more clear view, we can see that we can actually generate different curve or phase and magnitude in the phase, and based on this intersection point. So we start from omega equal to zero point 0.2, omega equal to 0.4, zero point 0.6. So different intersection you can figure out with your angle line, okay, as well as your magnitude line. So one point is whether you have noticed or not, magnitude is increasing. In some curve, it is actually tangent. So wherever it is tangent, this is actually giving you the peak value. Okay, so tangent is giving you peak value. So in this particular case, tangent is at 0.8. So at 0.8, we are able to 0.8. We figure out the value of the peak value of the frequency response of the closed loop transfer function. So some other value as well you can try, and similarly the magnitude is now. So magnitude increasing, then it is again going to the decreasing curve. So maximum was an intersection with 5 dB, then it is again going to minus 3 dB, then 1 dB. So this is how it is going. And also you can find out 0 omega phase margin and the gain margin. So we know that for the gain margin, actually you have to figure out minus 180 degree crossing. So minus 180 degree crossing, you can say it is happening around 1.5. So at 1.5 approximately, here 1.5, 1.4, you are having actually 0 dB crossing. So here. Okay, so that will give you, if it is a so somewhere here, around here, So it will give you the gain margin. Okay, so gain margin. And at 0 dB, in this particular case, actually at 0 dB change, whatever the angle remaining from minus 180 degree, this is your phase margin. Okay, so this is one thing. So we figure out what is your phase margin frequency. Now, what about the gain phase margin frequency here? So actually it is related to 0 dB crossing line. So what is our 0 dB crossing line here? As you can see that our 0 dB crossing line is approximately somewhere here. Okay, so it will be going through this line somewhere here. Okay, so it will give you say approximately 1.5, something like this. So which is evident here as well. Oh, sorry, it is in between 1 and 1.2. So approximately 1.2 maybe. Okay, so this is how you have to figure 1.1 somewhere here. 1.1 maybe. So this is how you can, from this Nichols diagram as well as from the open loop frequency response in dB, basically from the board plot, you can find out the closed loop frequency, magnitude, and the phase response. So now next is a relation between the closed loop transient response and open loop frequency response. So how can we figure out the relation between the closed loop transient behavior as well as your open loop frequency response? So for that, what we can figure out here is that what is the relation between the phase margins. So for this, we have to find out the phase margins. Phase margin, we already know, whenever the magnitude is 1, at that point, whatever the angle between 90, your minus 180 degree and your actual frequency phase, that is actually your phase margin. So to figure out that, the magnitude value actually has to be set to 0. Magnitude value is set to be 1 or 0 dB. So 1 or 0 dB. And then you have to figure out the condition of the omega that will give you that magnitude 1. And after finding out this value, we have to figure out what will be the phase. So phase minus 90 degree divided by minus 90 degree is coming because you have a S in the denominator. So if you bring it to the numerator, you're going to see that there will be a pole and a 0. So there is one pole at origin. So the pole at the origin is actually contributing minus 90 degree. And this one is actually contributing this omega 1 by twice zeta omega n. So if after putting the value of the omega n, so this is what you're doing, and just applying some slight trigonometric identity, we are going to find out the phase margin. So basically the phase margin, which is a frequency, open loop frequency response characteristic, is related to our zeta value, zeta, which is actually related to our the transient behavior of the closed loop system. So if you plot these two, then we are going to find a relationship like the curve like this. So which actually depicts the relationship of your phase margin with respect to your damping ratio. Okay, so now before going into solving one math problem, we have to actually see how graphically actually we can find out what is our minus 3 dB or bandwidth. How can graphically we figure out? So as you can see here, minus 3 dB line is being shown here. Okay, so minus 3 dB line is being shown here, minus 3 dB line, and that is approximately in between 6 to 7.5 dB, minus 6 to minus 7.5 dB, and also the frequency range that we are going to see is that in between 220, 225 as well as 135 approximately. So within this range, if you have your frequency, then you can say that this is actually your bandwidth or minus 3 dB quotient. So this is what you are trying to figure out. 6 in between 6 and in between 135. But the curve is actually something with the magnitude curve. So the phase curve. So that is why it is in between minus 135 to, both the condition has to be fulfilled. In between minus 135 to in between 225 phase, and the magnitude has to be in between 6 to 7.5. So if those two conditions fulfilled, then actually it gives you the minus 3 dB line, or the corresponding frequency is actually the bandwidth frequency. So in this particular example, basically this is your example 11.13, 11.13, and it says that this is the transfer function that has been provided, and corresponding frequency response curve is given. You have to find out what is the value of TS and what is the value of TP, peak time and the settling time. These are the two quantity you have to figure out. So now, just in the previous figure, whatever we have seen, that at minor, whether our minus 3 degree line, that whether we can actually figure out or not. Okay. So minus, in between minus 6 and minus 6 and minus 7.5. So somewhere here actually we are minus 6 and minus 6 is, I think, this one, minus 6 minus 7.5, somewhere here. So in between here you have to find out the point that is actually will going to give you, and also then you have to verify the phase. The phase is in between also 135 and 220, so very close. So we can say that this frequency is corresponds to our bandwidth frequency, so omega bandwidth. So which is, we can say that approximately 3.7. So for calculating this one, two things we need. One is the bandwidth frequency, as well as the other unknown thing is our zeta. So if you know these two parameters, then you can easily figure out what would be the value of your settling time as well as peak time. So we already figured out omega bandwidth based on the condition of the previous diagram, that the magnitude will be in between 6 and in between 6 and minus 6 and 7.5, as well as your phase value has to be in between 1 minus 135 to minus 1 225. So both of them matches here, and it gives you approximately the bandwidth frequency 3.7. Now what about zeta value? Zeta value is related to the phase margin. We just depict the value here. So for that one, what you have to do, phase margin, when I can find phase margin is available at 0 dB crossing line. So somewhere here is actually we have our 0 dB crossing line. So 0 dB crossing line is this, is somewhere here. Okay, so the angle will be, this is your phase margin. So phase margin is approximately, we can say that 145 or 45. So minus 145 minus 180. So approximately 35 degrees your phase margin. So if 35 degrees is your phase margin, then on the phase margin you can easily find out the corresponding value of zeta. Okay, so this is how you have to find out the zeta value, and once you know the omega bandwidth as well as zeta value, so according to the book, it is zeta value is approximately 0.32. So if both of them are known to us, now we can easily put the value and figure out what should be the settling time. Settling time according to the book's calculation is 4.86 and the peak time is 1.43 seconds. So this is how actually you have to do the calculation. So relation between the phase and the damping ratio, relation between your frequency response parameter as well as time response parameter. So this sort of thing you have to relate, and based on that you have to do the calculation to find out the corresponding time domain values based on the frequency domain values. The next thing is your steady state. So how actually steady state characteristic can be related with our uh, frequency response. So these are the both diagrams. So basically based on the both diagrams, so we have to figure out. So what do we know that for zero order system? So for zero order system, what is the parameter that you have to take? Kp. Kp is basically limit s tends to 0 g of s. So we already have g of s here. So basically what we are going to get is Kp is nothing but limit. If you apply the limit, then we have K. Then you have multiplication of I equal to 1 to n zi, and then multiplication of I equal to 1 to m pi. Okay. So basically the common magnitude. So as already in one of the calculation of the board diagram, it said that initial curve, if it is a flat curve like this, it actually only gives this magnitude. So we can say that the value that we are getting initially from this flat curve, that is our actually Kp value. So it will be given in logarithmic 20 log Kp. So basically, you have to find out the anti-log of it to find out the actual magnitude. Now, how to find out? This is for type 1, so type 0. Okay, so type 0. Now, what about the next ones, type 1? So for the type 1, we have a pole here, and because of that pole we know that initially we'll have a 20 dB per decade decreasing line. Okay, so 20 dB per decade decreasing line. But for K, for this type 1 system, we have to use kV. kV is limit s tends to 0 s g of s. Okay, so same thing. Basically, what we are going to get is K. Then you have product of I equal to n zi, product of I equal to 1 to m ei. Okay, so this is our kV we already calculated. Now, if from our equation, what do you know? So from our equation, you can see that if you are interested about the magnitude only, so omega 0 will be there. We're not just considering the phase, only the magnitude. Omega 0 will be there, and then you have the magnitude here. So if it is not in terms of log, so only simple magnitude, so then what you are going to see that the simple magnitude m will be 1 by omega. Then you will have product of I equal to 1 to n zi. So all the zi multiplied divided by all the pi equal to 1 to m pi. So now if you can find out the 0 dB line, so whenever it is crossing intersecting with the 0 dB line, so at the 0 dB line magnitude is 1. So you can say that the magnitude is 1. So if the magnitude is 1, then this omega goes to the other side. So omega is becoming actually this parameter. Okay. So sorry, the k was also there. So this is nothing but our value of our kV. So what do we have to do? Whatever the initial minus 20 dB slope that we are going to find, that we have to extend up to 0 dB line. So whenever we have an intersection point, the omega of that intersection point is actually equal to our kV. So from the kV, we can find out the steady state error. Now, what will happen for the type 2 system? The type 2 system, this is our frequency. So if you only consider the magnitude, then what you are going to get is 1 by k omega square, uh, uh, product of I, because of the fact we already similar idea. So limit s tends to 0 s squared g of s. So basically k, then product of all zi and the product of all pi, isn't it? So this is k. So now if you only consider the magnitude, then we are getting zi pi. So if we again find out the 0 dB crossing line, okay, so for the initial slope of minus 40 degrees, so if the minus 40 degree initial slope, so because of the two pole, for one pole we have 20 degree, because of the two pole we have 40 degree slope line. So with 0 dB crossing line, the magnitude is becoming 1. So basically what we are going to find is this value. So now if you take it to the other side, this is what we have. And now this quantity is nothing but our value of k. So we can say that omega square is actually equal to Ka, and omega, that whatever the omega we are going to find here is actually root over 1 by equal to root over K. So what we have to do, we have to extend our curve to find out the 0 dB crossing line, and whatever the corresponding value of the omega, that omega we have to figure out, and that is nothing but your K. So Ka will be basically omega square. So idea will be more clear with the example. So let us look at this example. So in this first example, as you can see, initially actually what we have a constant line. So what does it say? It says that your type of the system is 0. So what will be the value, the magnitude 20? So we can say that 20 log Kp should be equal to 25. So Kp will be, just do the calculation. So it will give you 17.7. Now in the next curve, as you can see here, actually we have a minus 20 dB line. So what does it mean? It is a type 1 system. Type 1 system. Then we figure out, we have to extend that 20 dB line to the 0 dB 0 dB crossing line here. Sorry, not this one. So the 0 dB crossing line here. So and corresponding frequency we have to calculate, figure out, and you can see that it is almost 1. This is 0 0.1, 0 0.2, 0 0.3, 0 0.4, 0 0.5, somewhere in between 5.7 or something like that, 0.57 or something like this. So this is actually equal to your kV. Whatever it is, whatever it comes in the middle. So this is what we are going to get. Next one, as you can see, initial curve that we have, initial slope is actually having is minus 40 dB per decade. And that gives us the information that the type of the system is actually 2. And we have to extend again that initial curve up to the 0 dB crossing line. And in this case, I can see that it is 1, 2, 3. So basically, at 3, omega equal to 3, we are actually having 0 dB crossing. So we know that omega equal to root over k. So k is omega squared. So basically k will be 9. So based on that, you can easily calculate what should be your steady state error. Okay, so in some system, we are going to see that there is a delay. So if you have a time delay in your system, sometimes in the minor loop, sometimes in the feed forward part, we have some delay. So what will be the impact of the delay of ours on our system? So let us deal with a general system input that we apply through the system G of S, so we get the output. So in another system, we have the transfer function G of S, which actually have a delay of t seconds. So we can say that our output will be c t minus t, small t minus capital T. So now from the Laplace transformation, we know that we can be including our delay in terms of this. So e to the power minus st. So don't get confused about this one. I'll just copy it from the book. So it is actually e to the minus st cs. So whatever the actual response was there, with that we have our delay, Laplace transform version of the delay. So it was the first system, it is the second system. Now if you compare these two systems, so then what you can see that the delay system is actually actual system transfer function, and with that we have this delay element e to the minus st. So now if you want to go for magnitude, this is actually only the angle contribution. So magnitude will be remaining as it is, but what will be the value of the phase? So it has two components. So this is one component, this is another component. So the magnitude is the same as previous one, the magnitude of this one, but the phase is having now the phase of this one, as well as additionally we have a decreasing phase of minus omega t, minus omega t. So basically, if you figure out the phase will be simply added. Since it is minus, so it is minus is added with that particular phase. So phase of the g of s. So whatever the original phase angle we had a linear decrease of phase, because we are plotting in terms of the frequency omega. So we have a linear relation decrease of phase will be added there. So if you look at this diagram now, based on the fact that we have seen, so phase plot is remaining as it is. So say without a delay, this was our curve, and without a delay, this was our curve. So we can say that from omega 0 dB crossing line, we can find out our original phase merging, this one, and from the 180 degree crossing line, minus 180 degree crossing line, we can find out our gain margin. So according to this one, it says that only if you have a delay, only the phase angle will be changed, and which will be reduced linearly. So if you incorporate that linear decrease, so this will be becoming your new phase plot, and the new phase plot says that your at 0 dB crossing, your phase margin is actually reducing. And also, whether you have noticed or not, even though the magnitude plot is remaining unchanged, but our 180 degree crossing point is also changed. Previously it was here, now it is here, and because of this, we can say that our gain margin is also reduced. So directly it is not reducing gain margin, the delay element, but it is actually shifting our minus 180 crossing point closer, bringing it closer. So because of that, our gain margin is also reducing. What does it mean? The delay element will actually make our system closer to unstable zone, or actually it will be more and more vulnerable, and it will be trying to go into the unstable zone. Okay, so so far I think you what I explained in the last class, that if from the phase margin, how to find out the stability of the system. So if you have something like this, if you have a plot like this, and at say this is happening at 180 degrees, so 180 degrees, this is your crossing. So at this point, if your gain is more than 1, and gain is, this is your 0 dB line. So if your gain is more than 0 dB line, then actually our system is unstable. So for 180 degree crossing line, the gain has to be lesser. Okay, so say we have a plot like this. So now at 0 dB crossing, our gain is actually smaller than your 0 dB line. So negative values, maybe minus 40 dB or something like this. Okay, so because of the delay, now this point is shifting there. and because of which our gain margin is reducing. If you have a more delay, so it will be going more and more. Eventually, what will happen is 0 to the percent line may be giving a positive value of magnitude, and which will actually drive your system into unstable zone. Okay, so experimentally, how can we actually figure out our system transfer function? So is there any way to find out system transfer function experimentally? So a lot of things written here. I think you will just have to go through that one. It is not a method that actually can be implemented in pen and paper. It is difficult to implement. So it will not be that important for the exam. We actually have to go into some program like MATLAB to implement this method. So bottom line is, if you have a curve, given curve, then actually you have to see whether there is a peak or not. So as you can see here, we have a peak at 5. So this is peak is only occurring for second order system, and the frequency corresponding to that one is 5. So basically this is your omega n, and also from this height, which is approximately 6 or 5 degrees, 6.5 degrees dB. So that will give you corresponding, this height is actually related to your zeta value. So we can find out a corresponding zeta value of 0.24. Is it okay? So from this one, we can assume a unity gain system, a second order system maybe there, and that second order, say G1s is something like this. Omega n square, there is 25 s square plus 2 zeta omega n s. That will be approximately closer to 2.4 s plus your 25. So what will be the next approach? So we predicted that we have a second order system here. So from this original curves, we have to plot the curve for the second order system, and from this original curve, we have to subtract that curve. Then we are going to get the next curve. And the next curve, you have to look for whether there is any other peak. So since there is no other peak, we can say that there is no other second order system. Then we have to look for whether there is any first order system. So we can see that in between this, we have a 45 dB per decade decrease here. So at the middle point is actually should be our break point, and if it is a decrease, then it actually represents a pole. So first order a pole will be there, and which is happening here, which is actually 90 at frequency X is 90. So actually for unity feedback, say this is your G2S. So we have G2S equal to say 90 by S plus 90. So why we are actually having this one? Because we have to take common of the 90. So we have to make it 90, 0 by 90 plus 1. So a 90 will be there. So this is actually that 90. So it will be cancelling each other. So we figure out that there is a first order system, something like this. Now, what do you have to do? From the original plot, you actually have to find out the plot of G1 and G2. And then from the original plot, you have to subtract those G1 and G2 plot. And then you're going to get this curve. And this curve actually from the phase, as you can see, there is a decrease of almost 45 degrees. Then again, have your 45 degrees. So this is actually represents a lag compensator. Lag compensator. So why lag compensator? So in the lag compensator, we said that pole will be closer to, pole is closer to origin. So basically we have something like this. S plus, say if it is S plus 5, then it is, the other one has to be slightly higher. Okay, so basically at 5 break frequency 5, you will have a decreasing nature, and then it will stay for some time. Then at break frequency 10, it will be again increasing. So eventually your phase value will be something like this. So this is what we are seeing here. Okay, and the line of the line that we are figuring out here, two break frequency, one break frequency is here and the other break frequency is here. So this is one break frequency is actually 9 and the other break frequency is actually 20, 30. So basically what you can see, the pole has to be closer. So S plus 9 and we have S plus 30. So the magnitude again has to be normalized, and I think it is approximately 0.3 if you take common, and 3.03 0.303, something like this will be happening. Okay, so we figure out the three functions. So this is your G3S. So you figure out G1S, G2S, G3S, and then we actually verify with our actual system, which is more or less same. So you look at the in both the equation 10.89 and 10.90. So they are almost close to each other. So this is a way of figuring out transfer function based on our frequency response plot. So this is the last. This was the last topic of your chapter 10. So which has to be actually figured out in terms of some software like MATLAB. Okay, I hope this will be the end of the syllabus for the semester final exam. And even though one chapter left, I will try to cover it with another video and conceptual part of it, and I will try to upload it as soon as possible, inshallah.